Hey everybody, I hope you're doing well. In this video, I want to talk about a related rates problem, specifically the ladder problem, and we're going to be doing two different questions for a falling ladder. So let me get started. Okay, so here's a situation. We have a wall and a ground, and I'm going to assume that this wall is perpendicular to the ground. And I have a ladder that's leaning up against the wall. So what are some facts about this ladder? The length of the ladder. I'm going to say this is 13 feet long. And the bottom of the ladder, well, that's actually going to be slipping away from the wall. And it's going to be moving at 2 feet per second. My question is, how fast is the top of the ladder sliding down when the bottom of the ladder is 5 feet from the wall? So I want to figure out the top of the ladder. I want to figure out the rate at which it's falling when the bottom is 5 feet from the base of the wall. That's my goal. So let's try to set this up. Step number 1, draw a picture. I did that already. Step 2, label everything we can. The distance from here to here, I am not going to label it as a 5. Is this ladder moving? Yes. So is this distance dynamic? Is it going to be changing? Well, yes. I'm going to label it with an X. The height of the ladder, or the height above the ground, that's also changing, so I'm going to label that with a Y. What part of this triangle is not changing? Well, the length of the hypotenuse is not changing, so I'm going to label that with a 13. The goal here is to figure out how fast is the top of the ladder falling. So what's the relationship between X and Y and 13, if we can come up with one? Well, you may have seen this before. The Pythagorean theorem. I know that the bottom, that's labeled with a Y. That's labeled with an X. So I know that dx dt, that's equal to 2. Because this distance here is increasing at 2 feet per second. The goal is to figure out what dy dt is. That is the unknown thing here. How do I get these derivatives incorporated into this model? Well, let's take the derivative of both sides of this model with respect to time. The derivative of x squared with respect to time, 2x dx dt. The derivative of y squared with respect to time, 2y dy dt. And here's a common mistake. What's the derivative of 13 squared? It is not 26. The derivative of 13 squared is 0. So at this stage of the game, I have a derivative equation here. I have one piece of knowledge. I'm trying to figure out the other piece of knowledge. I can do this when x is equal to 5. Now I should plug in 5. If I plugged in 5 earlier, this would have been a 25, and this all would have been 0, and well, that would have been a bad idea. If x is 5, are we able to figure out y? 25 plus what squared is equal to 13? 25 plus y squared is equal to 13 squared is 169. This tells me that y squared is equal to 144, which tells me that y is equal to 12. I'm taking the positive version of this because, well, it's a distance. I can't have negative 12 there. So now I know what x is. I know what dx dt is. I know what y is. Well, the only thing that's unknown is the dy dt. So now I have to plug some stuff in. 2 times 5 times 2 plus 2 times 12 times dy dt is equal to 0. So what does this give me at the end? This says that dy dt is equal to negative 2 times 5 times 2 all over 2 times 12. We can do a little canceling here. This 2 with that 2, this 2 with the 12, I'm left with a 6. So dy dt is equal to negative 5/6. What are the units? Well, the units for y, that was measured in feet. The units for time, that was measured in seconds. So if the top of the ladder is falling at a rate of 2 feet per second, and we do this at specifically when the bottom of the ladder is 5 feet from the base, the top of the ladder is moving downwards at 5/6 of a foot per second. That's what this negative sign means. Y is getting smaller. This distance is getting smaller. At the beginning of this video, I said I was going to do 2 problems. But I think this is long enough right now. I'm going to break this up into 2 videos. So for the second problem, well, just go to part 2 of this ladder problem series. I hope this was helpful. If you got a question, let me know. Have a great day. Bye.